Okay, let's get started then. So we are happy to have Prudhvi Bhattiprolu from Michigan here today. Prudhvi did his PhD with Stephen Martin at Northern Illinois University, and he's about to go to Italy in a few months to join the groups in Florence and Rome. So Prudhvi is going to be telling us about all sorts of things minimally beyond the standard model. So take it away, it's pretty awesome.
Thanks, Robert, and thank you everyone for being here. So I'll talk about some of my work with my PhD advisor, Steve Martin, Aaron Pierce, and James Burns at University of Michigan. And I'll try to take a bottom-up approach to building BSM theories. And in particular, I'll be looking at simplest extensions to the standard model, and especially to the fermionic sector, maybe vector-like leptons, and then to the scalar sector, I'll talk about what the depleted Higgs mean, and also talk about supersymmetry a bit, and from the perspective of gauge coupling unification and what it implies for the superpartner masses, and then I'll conclude at the end. So, although the standard model is now complete with the discovery of the Higgs boson with a mass of 125 GeV, we know that that's not the full story because there are still many mysteries that needs to be addressed. In particular, there is the electroweak hierarchy problem, which is the origin of the weak scale. Why is that scale so much more lighter than the Planck scale? There is the strong CP problem, where we expect the CP violating QCD vacuum angle theta to be of order 1, but experimentally that's not the case. There is also the question of dark matter abundance that has to be explained. And then there are a lot of different other problems, which I won't go into detail. And I apologize if your favorite problem is not in here. So assume those are all in these 3 dots. And so the standard model particle content that we know and love doesn't explain these mysteries. And so many models that address these issues often predict new particles, both to the scalar sector, fermion sector, or even the gauge sector. In this talk, I'll just restrict myself to the scalar and fermionic extensions to the standard model. So first, I'll start with the fermionic sector. And the natural extension that one could think about is 4th generation chiral leptons, which is just like the standard model, in a sense that the left and right-handed pieces transform differently under the SU2 cross U1 symmetry. And if I have left and right transforming differently, then the anomaly cancellation is not so trivial. And in order to give these masses, because if these are lighter, we would have already discovered them. But since that's not the case, these have to get masses through the Higgs coupling. And in order to avoid discoveries in the past, the Yukawas have to be very, very large. And because of this chirality, or because of the chiral nature, these do not decouple from the flavor and precision observables, namely the STU observables. And these also do not decouple from the Higgs production and decay. So what are the 2 great achievements at the LHC? One is the discovery of the Higgs boson, and the other is it ruled out most of the non-decoupling theories, including the theory of SM4, or the 4th generation chiral fermions. And the only theories that survive are the decoupling theories, where by that I mean if I make the mass scale heavier, these decouple from the standard model. And the examples of some of these theories are, for example, vector-like fermions and supersymmetry, whether we like it or not. So what are vector-like fermions? So these are fermions where the left and right-handed transform the same way under SU2 cross U1. And these are automatically anomaly-free, so we don't have to worry about that if we add more vector-like fermions in the theory. And since these are vector-like, we can actually have Dirac mass term. That is, we can have a bare electroweak singlet mass term to get most of its mass. It could still couple to the standard model fermionic sector. And if they do, these actually decouple from the flavor observables and the STU parameters like epsilon square over m square, where epsilon is the tiny Yukawa mixing with the standard model fermion sector. And these also decouple from the Higgs production and decay, like epsilon over m. And many BSL models propose the existence of these vector-like fermions, such as the ones that address the hierarchy problem. For example, supersymmetry, Higgsino's in supersymmetry are nothing but doublet vector-like leptons with specific couplings to gauginos and fermions. And then the models that address dark matter abundance. For example, neutralinos, in which Higgsino is a part of it, is vector-like, and then or singlet doublet fermion model where it has a singlet vector-like lepton and a doublet vector-like lepton that mix in a specific way. And also the KSVZ model that addresses the strong CP problem has vector-like quarks in them. And then there are also models that address the baryogenesis that require vector-like leptons, or sorry, vector-like fermions in general. And there are models where you could write down a vector-like lepton that couples to the muon, and that could address the muon G-2 anomaly.
Is KSV carbon?
Sorry?
Is KSV fermion carbon?
No, it's vector-like.
Why is it from carbon?
Sorry?
It's carbon with attachment.
Oh, sorry, I mean vector-like under the standard model gauge group.
Gauge group.
Yeah, under the gauge group, it's vector-like.
And let me ask one question.
Yeah,
when you impose the mass to vector-like fermions, do you impose quantum mass, or you just take it as a free quantum?
Yeah, it's just a free parameter. So it's just a Dirac mass term. So it can be.
Is it stable to irradiated pressure?
I mean, these.
If you take that as a free quantum, do you think it's stable to irradiated pressure?
Sorry, I'm not sure.
I mean, Dirac masses in general.
Yeah, but given the quantum mass as a top scale, I think a natural scale for the bare mass of the vector-like fermion is one scale. So I'm asking if you think that as a free quantum.
It's just a free parameter.
It can be a free quantum. People normally do that, but I think is it well justified?
I'm not sure why Planck mass.
Is it consistent with the, for example, other like setup of the theories like radiated pressure?
Yeah, I think it is, right? Because it's.
I'm not sure. So I don't.
Yeah.
know. I'm asking to you if you take the option of having that as a free quantum.
I think there shouldn't be any issues. It's just a Dirac mass.
You're worrying about yeah. If you do you have some mechanism to impose the mass of the vector-like fermion? Like so you use some singlet scale. Some skill. I don't need to, but I'm just asking your attitude, because I think there's two options for the bare mass for the vector-like fermion. You can take either the cutoff scale, point scale, or you can take it as a free quantum. If you take it that, because you answer you take that as a, you treat it as a free quantum, I'm asking.
I mean, I'll just take a phenomenological approach.
Yeah.
I mean, the term is preserving the gauge symmetry, so I can write down the term and there's no problem with it. The only constraints would be from the experiments. And so as long as they are in line with the experimental constraints, there is no issue in having whatever mass we like.
There's no.
It's like the new term, like
It's me, yeah.
you can take whatever you want.
I'm just asking because I'm not sure. But you're saying it's okay.
Yeah, I mean, it's a
it
Dirac
can be
mass term.
consistent with other theoretical setup, including radiated pressure. It can be stable, for example, to the potential radiated pressure.
So when you say stable, like these don't decay?
Stable means like you're sure for avoiding the radiated correction to the mass to the vector-like fermion, which is larger than the bare mass. You're sure for
That's guaranteed.
Yeah, I think that's guaranteed, right?
that's guaranteed.
Yeah, I mean, that's like chapter 3 of custom control.
Like
pyrosymmetry.
Yeah,
Right.
that's why scalars
from the symmetry argument.
scalars are confusing because. But
I mean, the left and right.
I see.
Yeah.
Yeah, the left and right transform the same way. So I can write a Dirac mass term and there is no issues with that. Unlike the chiral fermions where you need to have a Higgs coupling in order to get its mass.
I see.
So yeah, so there is no issue in writing a Dirac mass. Okay, thank you.
Separate question. So it seems like you're classifying new degrees of freedom in the standard model based on their like standard model charges, like how they transform into U1, SU2, SU3. But I can add, there are tons of like new degrees of freedom I can add, which don't have any charges under those things, but still coupled to the standard model, like axions or like a dark photon with a kinetic mixing, or even like a fermion with like a magnetic dipole moment or something. Like how do those things get captured by your story?
I mean, so far I'm just talking about the fermionics sector.
Yeah.
So any new fermion that you have in the theory has to be vector-like.
Yeah. I mean, I guess I don't disagree with that claim, but maybe I'm sort of jumping the gun. But it seems like you're going to try to be classifying things based on like having coupled in different gauge groups. But like I could imagine, like I think if I have a fermion which is a complete singlet under this standard model gauges, I can still write down like a magnetic dipole moment operator under E&M, and like that's still an observable. But like, is your story gonna cover stuff like that too?
No, I'll just talk about three like simplest things. I mean, yeah, there are a lot of. I mean, the word simple is controversial, but then like but I'll just talk about things that I've worked on, and these are the things that I've worked on. But you can have infinite number of possibilities.
Okay.
But all I'm saying is, if it's a new fermion, it has to be vector like under the standard model gauge group. You can have new gauge groups, but then they can transform differently under that. But under standard model, it has to be vector. That's the only statement I'm making.
Okay.
Thanks. Okay, so how do we go about probing these? Well, it's sometimes argued that hadron colliders have the best discovery reach for these particles, and on the other hand, lepton colliders could be used for indirect searches and precision studies. And this is plausible for strongly interacting particles, for example, like vector-like quarks, where the bounds are well above TeV scale. For example, here are the bounds on T prime, B prime that are assumed to mix with top and bottom quarks. And then this is the psi 0 prime, which is the vector-like quark in the KSVZ model, for example. And we obtained a bound in one of my recent papers with Robert and Gilly and Aaron. And by the way, since this is an electroweak singlet, these are actually long-lived particles in a collider. So you can use R hadron searches to sort of constrain these. So for vector-like quarks, I agree that the hadron colliders have the best discovery reach. But on the other hand, it might not be the case for weakly interacting particles, for example, like vector-like leptons, and especially for the singlet vector-like leptons that still has charge under electromagnetism. So for the doublets, it's constrained to be all the masses below about a TeV scale are excluded at 95% confidence level. And whereas for the singlet, there is a lep bound, which is 101.2 GeV. And then CMS recently ruled out 125 to 150 GeV. And here I'm assuming that the vector-like leptons are mixing with the tau, which is actually a pessimistic approach slightly, because if you couple to muons or electrons, you could do much better. But in those cases, the flavor violating constraints would be much stronger.
Oh, sorry, Prudhvi, those greater than or less than?
I mean, sorry, I'm just talking. So here I just have the allowed parameter ranges.
Oh, allowed, okay.
Yeah, sorry, yeah. So these are the allowed.
Okay, yeah, sorry. So, yeah, okay. So everything below 150 except for this, there's an interesting window where it's still.
Yes.
Okay.
So there is a window from 100, roughly 100 to 125 GeV that's not yet probed, and then anything above 150 GeV is still possible.
Maybe you'll end up writing a Lagrangian later, so if that's the case, forget this. But what does this mixing look like? Given that these are vector-like, and the top or bottom are chiral.
I mean, you would still write a term that's like this. Like this would be the mixing term, where the tau prime is a vector-like lepton. Oh, sorry. I mean, I have to be careful. This is for the doublet. If I'm writing T bar, but I could write it for the singlet, where it's
So in the doublet case, the new lepton is taking the place of the usual doublet. It's still vector-like, but you can start writing those kinds of terms. Right, in the singlet case, vice versa. So it either looks like a left-handed lepton, but it's still vector-like. So you can start writing eucalyptus with it, or it looks like a right-handed.
And it looks vector-like because you're also.
And it's still vector-like because you're still assigning the same charge to the left and right.
Yeah, but you're also.
But you can start,
another
but yeah, you can,
right-handed.
you start writing eucalyptus.
Okay,
Yeah, I mean, these are the terms that are still allowed by the symmetry, so you can still write down these things, because I want these to decay. And if that is the case, these are the terms that I could use to that facilitate the decay of these vector-like fermions. But I'll show you the mass mixing matrix in a.
And you can also do, like those terms, it's duplicated for both left and right components of the new thing. Because like the left and right are charged the same.
Yes, but I just need to write down one of the terms. So if it's a doublet, I can write down this term. And if it's a singlet, I can write down this term. But since.
Yeah, but sorry, I guess all I'm saying is just like Sarah's point is that you're not, when you write down like, let's say the top term in the doublet case, you're not like only projecting out like the left or the right. The top.
Yes, yeah, that's true. That's true. Yeah.
but you have that term, and then you also have a direct term for the tau prime.
Yes,
Which
so-
has the tau prime and.
Yes,
called
yes.
Tau prime, right?
Yeah, so you'd have to diagonalize to get the physical masses. But as long as the Dirac mass term is much, much heavier than the Yukawa, you're assured that it decouples from standard model if you make the Dirac mass heavier.
Oh, yeah.
Yeah, so the Yukawa has like, there are still constraints, which I'll talk about in the next slide for the singlet vector electron.
So it kind of looks like C star. Maybe.
Okay, so yeah, so I'll now focus on the singlet vector like leptons and argue that E plus E minus colliders can actually act as discovery machines where the reach for the same particles is not so great at hadron colliders, including future PP colliders. So these are these charged SU2L singlet vector like leptons. So this is the charge assignment under the standard model gauge groove. And then if I want these to decay, then I can assume the mass mixing of the tau prime and tau, and this is the mass mixing matrix. And the moment I write this down, I have constraints from decays of W, tau, and Z, which are over here. And if I make the epsilon too small, then this doesn't decay within the collider lengths. So I'll assume that the mixing is tiny, but still allows for prompt tau prime decays within the collider length scales. And with that, I now have a prediction for the branching ratios of tau prime as a function of its mass. And tau prime can decay to W neutrino, Z and tau, or Higgs and tau. And here we can see that the branching ratio for W and neutrinos is the largest. And we can also see that as I increase the mass, the branching ratios approach the Goldstone equivalence. And there are already papers that talk about its limited reach, the limited reach for tau prime at the LHC, for example, in this paper, and future PP colliders, which is a paper I've written with my PhD advisor. And even for 100, even with 100 TeV PP collider, the reach for tau primes is not so great. And that's because of this unfortunate large branching fraction to Ws and neutrinos, because I'm missing energy in my final state most of the time. And so it's very difficult to tackle this problem.
There's no dependence on epsilon.
Yeah, the epsilon dependence just drops out in the branching ratios. So
If epsilon is 0, do I still have tau prime to W tau?
no, sorry.
So it doesn't drop.
Oh, sorry. I mean, it is still within the assumption that epsilon is large enough such that it decays. So these are the, for example, this is the decay length. Sorry. Yeah, if I want the decay length to be 1 micrometer, then this is the limit on epsilon. And so I'm assuming that the epsilon is large enough such that it still decays promptly within the collider length scales, but small enough such that to avoid these constraints from W, tau, and Z decays. So it can be anywhere in here. And
So the branching ratios don't depend on whether it's between 10⁻² and 10⁻⁵.
yes, yeah, it doesn't, because branching ratio goes like epsilon squared for all of these.
Okay.
And then if I take the ratio, it just cancels out. Yeah.
So in this case, so these are, when you have doublets here, you have now actually, I guess it doesn't matter.
Oh, sorry, it's a singlet that I'm.
Oh, you're looking at the singlet.
Yeah, I'm just looking at the singlets because those have the very limited. Yeah, those are the ones that have very limited reach at hadron colliders. And on the other hand, I'll argue that E plus E minus colliders, we can measure its mass, and also I'll talk about how to measure its branching ratios.
No, I was just wondering about the doublet case, where you also then have a neutrino.
Yes, so in the doublet case, I think the Z. Yes, there is a neutrino, but if we assume just the mixing between the doublet and the tau, then the neutrino just decays to W and the tau. And then the tau
neutrino has the same mass as the tau.
Yeah, it has the same mass up to radiative directions. Yeah, so those would be degenerate if it's the doublet case. And there we can actually have very like good reach at LHC and also at future.
Okay, and you don't worry about Z decays to the neutrinos because they're heavier. Presumably they're taken heavier.
Yes, yeah. Since these are degenerate with tau prime and there is a constraint already that, yeah, these have to be heavier than TeV scale. Yes. Thank you, that's good. Yeah, so these have limited reach at hadron colliders, and that's because of low pair production cross section and also, unfortunately, large branching fraction to W and missing energy.
So sorry, one question. Epsilon V is coming from the
It's from the
riding the tau coupling to one of those, right?
Yes, so
Yeah,
it's yeah.
Yeah. So my question there is, why can't epsilon be larger than 1?
Well, there are constraints.
There are constraints.
I mean, if you take larger than 1, there are also
so in principle that's possible, right?
well up to perturbativity, sure, but then there are constraints.
Okay, so that's,
I mean, yeah. So there are already constraints that
I see.
yeah, that constraint that. So that's ruled out.
Okay.
Yeah, so we can live anywhere below.
Those are presumably from like precision cases.
Sorry, which ones?
Yeah, the constraints on that.
No, those are from the decays of the W, tau, and Z. Because now you, the moment you write down this mixing term, then also the standard model tau behaves slightly differently because those also get, I mean, has some component of tau prime. And because of that, you could mess up the branching fractions for W, Z, and tau. Yeah, so it's from that we can infer what's the bound on epsilon. Good question. Yeah. Okay, so at an E plus E minus collider, the pair production of tau primes proceeds through option photons and option Z's, and here is the pair production cross section at various E plus E minus collider energies as a function of its mass, and the current exclusion is shown here in gray by CMS, which was from 2022, just a couple of years ago. And here I'm just assuming that the beams are unpolarized, but you could also polarize the beams, in which case, so here the dashed and the dashed dotted lines maximize the cross section at click and ILC, for example. But for the purpose of this talk, just for demonstration, I'll just talk about unpolarized beams, but the results can be easily, yeah, the conclusions would still hold for other polarization options. And we've also accounted for initial state radiation and beam swelling in computing the cross sections and also generating events, which I'll talk about in a little bit. So now, since tau prime decays to z tau, Higgs tau, and W and neutrino, we have 6 different final state topologies. There are 3 different final state topologies with 2 taus in the final state, and then there are 2 different final states with 1 tau, and then 1 final state where it's just neutrinos and therefore the missing energy. And due to the large branching fraction to W and neutrinos, the W plus W minus with missing energy is the largest signal component. And since there is no, I shouldn't say no good strategy, but we have actually not tried to, we did not try to reconstruct tau prime masses in this last final state. So I'll just be focusing on the first 5 here. And we've also considered various backgrounds as allowed by kinematics. So TT bar and its associated productions with Z and Higgs, diboson processes, triboson processes. So these are all the backgrounds that we have considered. And we generated events at leading order while accounting for initial state radiation and Wheatstrahlung using the standard tools, that is fine rules, Wizard, Pythia, and Delphis for detector. So Delphis for detector, for modeling the detector. And so the model files that we are actually using are also that we built are currently being used by both Atlas and CMS to search for vector-like leptons, both doublets and singlets currently. And the goal for the first part of this talk is to reconstruct the mass peaks in various different final states or various signal regions. And for the purpose of this talk, I'll just talk about 500 GeV E plus E minus collider with unpolarized beams. And we have considered 15 different signal regions, all of them satisfying these 2 constraints, where the number of leptons and number of jets, the sum of number of leptons and jets is 4, and then the number of taus could either be 1 or 2, depending on which final state that we are targeting. And we reconstruct Z from leptons and jets, Higgs from BB bar, and W from jets in the final state, in the signal regions with 1 tau, with exactly 1 tau in the signal region. So for example, these are some of the signal regions that we consider, and each of these signal region targets different final states. So for example, 4 lepton 2 tau targets the ZZ tau tau, or 4B 2 tau targets the Higgs Higgs tau tau final state, and so on.
This might be a naive question, but do colliders actually see the tau or do tau decay?
That's an excellent question. Yeah, so the tau decays. So you would have to reconstruct the tau's 4 momenta at a collider, because taus could decay into neutrinos along with the pions. And so, yeah, so we also thought carefully about how to reconstruct the tau.
But can you reconstruct the tau if it's partly going to machine again?
Yes, you can. Because of so you can use collinear approximation, because if the taus are very, very boosted, then you're guaranteed that the neutrino that is released or emitted is almost collinear with the direction of the tau. So with that assumption, you can actually solve for the missing fraction. Yeah, and also since this is an E plus E minus collider, the square root of S is more or less fixed up to ISR corrections. So using both of these pieces, we can actually reconstruct the taus entirely. Yeah. And that's actually a major part in getting the right mass peak. Else the mass peak is all distorted. So yeah, that's a very good question. So I'll just briefly, I'll try to briefly talk about the peak reconstruction algorithm. So first we reconstruct the Z and Higgses, and then the W bosons, as I was mentioning in the last slide. We also rescale the jet momenta if these bosons are reconstructed from jets, such that the invariant mass of the jets is equal to the boson mass. And then at this point, once we have reconstructed the bosons, and then there is the tau, or the hadronic tau, we still have to account for the missing energy from the neutrinos. There are now various possible tau and boson pairings that are listed here in order to reconstruct the tau 1 prime and tau 2 prime, since these are pair produced. And the neutrinos nu1 and nu2, for example, nu1 is from the tau decay, And U2, if it's the signal region with exactly 2 tau, then that's the neutrino from tau decay. Or if it's the signal regions with exactly 1 tau, then the neutrino is produced in association with the W. But either way, we have to reconstruct the neutrino 4 momenta in order to reconstruct the mass of tau primes. So I won't go into this detail as to how we label 1 and 2, but I can talk more about that later if anyone is interested. So as you were asking, actually, so we use collinear approximation in order to reconstruct the missing neutrinos 4 momentum. So we use, with collinear approximation, you now have a handle on the 4 momentum of nu1 up to this free parameter r, which is the fraction, the momentum fraction that is taken away by the neutrinos. So you'd still have to solve for that. But up to that, we can also compute what's the 4 momentum of the other neutrino. And then we can enforce that both the neutrinos are on shell, so the masses are just set to 0. And in order to solve for this missing parameter r, we can just require that the 4 momentum of the reconstructed tau1 prime and tau2 prime to be exactly equal, and then further impose that the energies of the reconstructed neutrinos are positive. And so, yeah, once we have solved for r, we now have all of the four vectors in the event. And in case if there are multiple pairings, the tau boson pairings, then we can pick a pairing that minimizes the total 3 momentum. Because if there is no initial state radiation, then the total 3 momentum is exactly 0. And so minimizing this would give us sort of the right combination or the right pairing. And so here are the peak reconstructions in 2 different signal regions, namely 4-jet 1 tau and 2 lepton 2-jet 1 tau. And this is at 500 GeV, as I was mentioning. And on the right side, I'm showing the number of events if we assume the integrated luminosity of 500 GeV machine to be 4 Ataban inverse. And so different colors correspond to different input masses of the tau primes. And these are stacked together with the black shaded histograms, which are the backgrounds. And you can see that since tau prime mostly decays to W and neutrino, these 2 signal regions can act as discovery modes for these particles. And we can also see that the backgrounds are non-negligible, especially for 4-jet 1 tau, but it's still under good theoretical control. And there are similar peak reconstructions that are also possible in other signal regions. But I won't go into details about those reconstructions, but we can reconstruct that. So if the tau prime is discovered, then we can actually use the heights of these peaks in different signal regions to assess the branching fractions of these tau primes. So for example, this is the signal contribution breakdown in 4 lepton 2 tau and 2 lepton 2-jet 2 tau. And we can see that it's almost a pure sample of ZZ tau tau final state. So with this, we can have access to events in different final states. And similarly, with other signal regions, you can get a pure sample. For example, with these 2, you can get a pure sample of Z Higgs tau tau. And with these 2, you can get a pure sample of ZW tau nu final state. And also with the other 2 final states, we can get access to the other 2 final states as well. So with all of this information, we can also infer the branching fractions of these tau primes. So we can discover the mass and also get its branching fraction with an E plus E minus collider. And before I move on, I just want to note that both Higgs and top factories can also act as discovery machines if the tau prime mass is within the kinematic limit. So here are some demonstration plots, for example, for 250 GeV ILC on the left, not ILC, but 250 GeV, any 250 GeV machine on the left, and 380 GeV, which is the top factory on the right. So, so far I've talked about the minimal extension to the fermionic sector. I'll now talk about the scalar extensions. Actually, how much time?
A good amount. I would say at least 2 minutes.
Okay, great. Thank you. So far we know that the standard model Higgs is the only fundamental scalar in the particle content that we have. And as the Higgs measurements get more precise, there is a well-motivated possibility that these measurements could deviate from the standard model expectations and thereby pointing towards a complicated Higgs sector. And for this part of the talk, I'll focus on what I call the depleted Higgs boson, where the standard model Higgs boson acquires a universal coupling suppression to all of its final states and also gets an invisible width. And to set the notation, the delta is the universal suppression and delta square gamma inverse is the invisible width acquired by the Higgs. And the standard model Higgs is related to the observed Higgs in this way, where this delta is the universal coupling suppression. And at this point, it seems, it looks like delta and this gamma inverse are sort of ad hoc and put in, but these actually can naturally arise if you mix in the standard model Higgs with a real scalar singlet that perhaps decays to dark matter or with invisible decays in general. So, and to set another notation, so let's say if I define this parameter kappa inverse such that it is gamma inverse relative to the standard model width of the Higgs. And with that, we now have the production cross-section and the total width of the observed Higgs boson in terms of the standard model terms. And note that if I take delta to 0, then I recover the standard model.
Sorry, the kappa in, then is that invisible?
Yeah, that's invisible. Sorry.
Okay.
Yeah.
And what does the mixing operator look like?
So far, I'm just considering this in a general way, that if I assume that the standard model Higgs is related to the discovered Higgs in this fashion, then all of the production cross sections and the total widths are changed in this fashion. But you can get these if you add an additional gauge singlet that's a scalar and mixes with the standard model. I'll talk about that in later. Yeah, so far it's just general. I'm just assuming that if this is the case, then what do I get?
So this H just inherit all the one number of the small Higgs, but
Yes.
it has a different coupling.
Exactly. Yeah, it's just like the standard model Higgs, but it acquires a universal coupling suppression to all of its standard model final states, and then an invisible width additionally. And the LHC probes for the observed Higgs often report sigma times branching ratio relative to the standard model sigma times branching ratio in the visible standard model final states. And for the invisible cases, it reports an upper bound on sigma times branching ratio relative to the total standard model Higgs cross section. So with this data, we can actually now constrain both of these parameters, delta and kappa inverse. And so this is the current status of the depleted Higgs scenario. And just to remind, delta is the universal coupling suppression and kappa inverse parameterizes the invisible width of the Higgs boson. And so various shaded regions corresponds to various constraints from standard model searches at LHC. And then the dotted line here corresponds to constraint from Higgs to gamma gamma. And note that Higgs to gamma gamma arises at one loop in the standard model. And so these could be sensitive to new states, new particle content. And
sorry. Can I ask a silly question?
Mhm.
So you might also address this in a couple slides, but like, if I want to think of these two as independent things, can I do so? Because like, for instance, the standard model Higgs decays primarily to bottoms, which has a reasonably small Yukawa, and I could have some, like, because I see there's a factor of 10 there for kappa inverse. So I'm trying to think of how, like, maybe I could have a small delta, but still have a large kappa inverse.
yeah,
But if I have like a large Yukawa of my new singlet to some dark crap, then that's how I can have these two be kind of independent.
yes, so these are independent, but then the total invisible width is actually delta square times kappa inverse. So kappa, even if it is large, there is still a delta square suppression. I think that will be more.
Sorry, say that sentence again.
So the total invisible width. So kappa inverse is just a parameter. But the total invisible width of the observed Higgs is delta square times kappa inverse. So kappa can be large, but then there is still a delta square suppression. Sorry, all I'm
Yeah, sure.
yeah. So this is the invisible width.
Right.
Yeah, and I'll show in just a couple of
Yeah,
slides
okay.
that this actually arises naturally from mixing with the singlet that
Sure,
decays
sure.
entirely
Yeah.
invisibly.
Sure.
Really, sorry. Yes.
Yes, Peter.
So this depleted Higgs, this will perturb the thermal Higgs potential as well, right? If you replace the thermal Higgs field with the depleted Higgs, if you replace H thermal with 1 squared to 1 minus delta squared, little h, and then you will have perturbation to the, you will have a modification to thermal Higgs potential.
Yes, yeah, there will be.
But does that, is it okay to have such a perturbation to potential Higgs thermal Higgs? In terms of the stability of the electroweak vacuum thermal?
Yeah, I think as long as these are not large,
Because it seems like delta seems to be can be order of 0.1. So I'm wondering, yeah, if you allow for such a large delta, then I'm wondering if the electroweak vacuum can be stable to such a propagation.
I mean, as long as these are within constraints, I think it should be fine.
It should be fine.
Yeah.
Of course, it must be fine, but
Sorry, I mean, you're respecting the constraints, and so I don't understand the issue.
I think there's a separate concern you have that like, if I do MSSM or I do some SUSY breaking or something, I have conditions that are right down on my extended scalar potential to make sure that I reproduce the standard model. And so far here, you're just showing searches. So the question is about, yeah, like how would I draw constraints worrying about
Exactly.
reproducing the correct.
right.
But we need to see how it's coupled first.
Yeah.
Sorry, I'm not sure if I.
Yeah, maybe let's see the LeBron James. Let's see.
Thanks.
Oh, sorry. And sorry. Okay. Yeah. So this black shaded region with dashed borders corresponds to constraints from invisible searches. Searches for Higgs with invisible decays. And then here in dash dotted are some future projections with HLLHC with 3 Ataban inverse and 250 GeV-ILC with nominal running assumptions. And so you could constrain most of this parameter space with HLLHC or an ILC. And so far, these are just ad hoc parameters, delta and kappa inverse. But I'll try to make it more concrete. So consider a standard model with just one additional particle, which is a real scalar that is a singlet under the standard model gauge group. And after electroweak symmetry breaking, this is the scalar potential that you get, where m square is the mass squared matrix. And once we diagonalize this mass square matrix, then that leads to the physical states H and the exotic Higgs phi. So the standard model Higgs is now related to the observed Higgs in this fashion, which is what I was mentioning a few slides ago. So we can get this sort of depleted Higgs scenario with this mixing. And here delta is identified with the sign of the mixing angle that diagonalizes the mass matrix. And so here H is the depleted Higgs, which I was talking about, that gets this universal suppression, and also an invisible width in this fashion, where gamma invisible is the decay width of S to invisible states. And there is a new state, which is the exotic Higgs. And for simplicity, I'll just assume that H to phi phi and phi to HH are kinematically forbidden. You could also take that into account, but just for demonstration, I'll assume that's the case. And also, if you take m phi to be too large, then you could also run into constraints from precision electroweak and also just from searches for collider searches for the phi. So this is the 3D parameter space of delta, kappa inverse, and this new parameter m phi. This is not I'm not showing this to read off numbers, but just to show the richness of the parameter space. So the blue and the red curves correspond to the precision probes for the observed Higgs. The black curve are the collider searches for this additional exotic Higgs, and then the gold curves correspond to the Peschkin-Takeuchi constraints from STU parameters. So, and to understand this better, I'll just take two slices of it, one at kappa equals 0 and one at kappa equals 1. So these are the two slices in the 3D parameter space. So the gold dashed line corresponds to the constraints from Peschkin-Takeuchi parameters. And then the shaded regions here correspond to collider searches for the exotic Higgs at LEP, CMS, and LEP and LHC. And then finally, the dotted lines here correspond to the precision probes for the observed Higgs boson. And we can see, especially for the large kappa inverse case, we can see that the precision probes for 125 GeV Higgs is often more powerful than searches for the new Higgs states. Any?
So, I mean, kind of back to the earlier question, like you wrote down what the mixing looks like after electrosymmetry breaking, but do you have an operator that you could write in the unbroken theory?
I
just want to see what we're at.
Yeah, I think it's just some lambda times h square s square sort of the.
But then there must be a potential, so what do you think? In addition.
Okay, I think there's a new term.
So in addition to, okay,
So there is a term like this,
okay.
and then from that we get this sort of mass matrix.
But so then this should give you more complicated things than just a mixing. Then you'll also get like cubic and quartic terms.
That is true. That is true. You also get that.
But just, I guess, the point is the dominant effect is going to be the mixing, so you're not worrying about the effect.
Yeah, it's just focusing on just the. Yeah, I mean, also, I think this should be the dominant effect.
Yeah, that makes sense. But then I guess the Dongjun's point is you have to be careful about what lambda you choose here. Because if you choose the wrong lambda, then you might break. You might not get the right electron symmetry break.
Right.
Is S also getting a bad here?
No, S is not. Well,
I think in order to get a linear mixing between H and S, they probably both need a bad here.
Yeah, there's a question of if there's a cubic with like a SH.
I actually remember checking, but I don't recollect now. But yeah, I was just taking just treating this as an EFT where the Higgs gets these two suppressions and trying to argue from that point. But then, yeah, that's a good question. And maybe we can chat after the talk. I can try to look through my notes. Okay. Okay. And there are also future projections that are shown here by the dashed curves and the dashed dotted curves from ILC and HLLSC. For example, on the right plot, you can see that the 250 GeV ILC that probes the observed Higgs gives a stronger projection or much greater reach. Yeah, so if you have a depleted Higgs scenario, then I'm just arguing that just the precision probes for the Higgs can be more powerful than the searches for the additional states. Okay, so I'll get to that question after the talk, but yeah, if there are any other questions. Okay, so finally, I'll move on to supersymmetry and talk about the implications of precision unification on the superparticle masses. So what is supersymmetry? It's a symmetry that takes fermion to boson and a boson to fermion, and that essentially doubles the particle content of the standard model. So this is the standard model particle content. And if I add supersymmetry, Then I have the superpartners. So for example, so the first thing is you need two Higgs doublets in the MS system, just for anomaly cancellation reasons, in order to, and also to explain the masses of the up, down, and the leptons. So these are the Higgsinos, the superpartners of the Higgs. These are the fermions. And then there are squarks, which are superpartner to quarks, and then sleptons that are superpartners to the leptons. And then there are gauginos that are superpartners to the gauge bosons. And I won't attempt to talk about supersymmetry in any detail. There are excellent reviews that are listed here. So why is SUSY still interesting? Well, it can provide, first thing, it can address the origin of the weak scale, that is the electroweak hierarchy problem. It can also provide for the unification of gauge couplings. It can also provide a dark matter candidate, for example, the neutralinos, in order to account for the observed dark matter abundance. And it can also easily accommodate a light Higgs with Higgs mass of 125 GeV. But the biggest question is, where are the superpartners if SUSY exists at all? Well, we could have two answers, one from experimental and one from theory point of view. So based on LHC data, perhaps it's somewhere above TeV scale, although it uses some simplifying assumptions in making these claims. Whereas from the theory point of view, we must keep in mind that superpartners can get their masses entirely from soft breaking terms, and there is no reason why we should expect them to be of order weak scale, well, apart from addressing the hierarchy problem. That's still an issue, I agree. But in principle, the superpartners can be much heavier than the weak scale. And also remember that SUSY obeys decoupling. So the more massive I make the superpartners, the better it agrees with the standard model. So here I'll try to explore the implications of I'll just take the idea of gauge coupling unification very seriously, and then try to understand what it implies for superpartner masses in order to achieve precise gauge coupling unification. And I'll do it in three scenarios. One is MSSM with a common mass threshold M tilde, and then I'll consider, and I'll also do it in minimal supergravity, where there are 5 inputs at the gut scale. One is a unified scalar mass, M0, unified gaugino mass at the gut scale. There is tangent beta, which is the ratio of webs of the Higgs doublets, the sign of the Higgsino mass parameter, and then a universal scalar trilinear coupling, which is A0. So in our analysis, we set A0 to 0, and because we noted that if I have the SUSY scale to be much larger than the weak scale, then A0 has a very small impact on the spectra. And also in supergravity, in minimal supergravity, the gaugino masses have this simple relation. So if I have this M1/2, then I can find out what the gaugino masses are at low energy based on this relation. And with this relation, we also have a prediction for the ratios of gaugino masses. In particular, we can see that M1, which is the mass of the BNO, the superpartner of the B field. So BNO is the lightest gaugino in this setup. And finally, I'll also talk about the implications of unification in minimal anomaly mediation, where this is where the SUSY breaking is mediated by some conformal Weyl anomaly. And here there are 4 inputs: universal scalar mass at gut scale, the gravitino mass, tangent beta, and then the sign of the Higgs mass parameter. And in this setup, the gaugino masses is actually loop suppressed from the gravitino mass. And from that, we have a prediction for the gaugino mass ratio. And here in this in minimal anomaly mediation scenarios, BNO is the lightest gaugino. And we used SPHENO for generating the low energy MSSM spectra in these two high scale scenarios, the SUBRA and AMS. And it is well known that the gauge couplings approximately unify in the MSSM if I take the common mass threshold around the TeV scale, as I showed here in the plot. And in order to make and as a measure of the unification of gauge couplings, I'll define this parameter rho lambda, which is defined in terms of the gauge couplings in this fashion. And in standard SUSY guts, we can expect that this rho lambda minimum is of order 100. I won't go into details about that. And for precision unification, we actually require rho lambda to be much, much smaller than the expected values in the gut, in the SUSY guts. So we take that to be 20 just to be concrete. We can lower it or increase it, but just for demonstration, I'll just choose this value. And also this value corresponds to roughly 3 times the naive Planck scale corrections that you expect, which go like unification scale over the Planck scale. So with that constraint, here I have rho lambda parameter as a function of putative unification scale. And the black curve is the curve from standard model. And then the dashed gray line is the requirement for precision unification. And the various colored lines here are for MSSM with different choices for the common mass threshold, starting from MZ, which I'm just picking that for demonstration purposes. And I go all the way up to TeV scale. And we can see that in order to achieve precision unification in MSSM with common threshold, the mass threshold or the superpartner masses should roughly be in 1 to 10 TeV range. And these are the results in the high scale scenarios, namely in the minimal supergravity case on the left and minimal anomaly mediation on the right. And here I'm showing a plot for Sucra case, it's M1/2 versus M0. And for the anomaly mediation, I'm plotting the Vino mass, which can be related to the gravitino mass, which is shown on the right axis as a function of M0. So all the gray points that you see here satisfy the precision unification constraint and also reproduce the correct Higgs mass, which is 125 GeV. And we've also looked into regions of parameter space where the neutralino is the lightest supersymmetric particle, and then looked into cases where we can reproduce Higgsino and Vino dark matter. So we just did something very simple where we assume the R parity, and then we require that the LSP is neutralino, and then require that for the Higgsino dark matter, we require the mu term is around 1.1 TeV, whereas for Vino dark matter, the Vino mass is around 2.8 TeV.
And isn't a lot of that gray region excluded because U squared goes negative? Large M0 and whatever M1/2, if you run U squared, it goes negative. And that's why you're getting the Higgsino regions that are a couple of TeV, because if you go to the right of that, U squared goes negative, and there's no theory of it.
Sorry, is it true? So you're saying all of this parameter space?
No. I think everything to the right of the red dots is what I'm guessing.
I think so. I think we try to SP-Node tries to check for that automatically, and it cuts off around here.
I don't think so. But
Oh,
I think
I mean,
everything to the right there is probably not valid.
I see.
Just because U squared runs negative. It goes very fast, so the only way to get the Higgsino LSP is that you need now already mu to be relatively small. And if you move a little bit more in M0, you're already going into the, it's like where the focus point region is.
I see.
And so everything to the right or below it is probably not possible.
I see. I'll have to look into this. I see. Thank you. So here we can actually note that in the Sucra case, there is no Vino dark matter because Vino is the lightest gaugino, and so we just have the Higgsino dark matter points. Whereas in the AMSB scenario, Vino is the lightest gaugino, so the dark matter could either be Higgsino or a Vino.
I'm guessing the same thing happens here. That the left on the blue to the left of this is fine. But then again, everything to the right of the red points, so that's good.
I see. I thought maybe that was this line, but yeah, I should look into that. But thank you, thank you. Okay, so here we can now plot this quantity rho lambda, which is a measure of how precise the gauge coupling unification is, as a function of stop masses, which is a rough proxy for superpartner masses. And here we can see that for precision unification, the superpartners have to be roughly in the range of TeV to all the way up to TeV range, but up to the mu square target, which I'm. And finally, so here I have the rho lambda minimum as a function of the Higgsino mass parameter. And I'll just make a few remarks that most of this parameter space is unexplored by LHC or lies well beyond its reach. And from direct detection, dark matter direct detection constraints, we now know that the neutralino LSP, in order to be a Higgsino dark matter, it has to be extremely pure Higgsino. And from indirect detection constraints, we know dark matter seems to be less viable. With that, I'll conclude. So I tried to talk about few minimal extensions to the standard model, or some arguably minimal if you don't exclusive, but yeah. So I talked about the weak isosinglet vector-like leptons, where they have limited reach at hadron colliders. But on the other hand, if there is an E plus E minus collider, that can actually act as a discovery machine. And then I talked about the depleted Higgs scenario, where I argued that the precision study for the Higgs is often more powerful. And finally, I talked about the implications of precision unification on superpartner masses. Thank you very much. If there are any questions.
I know you were taking a bottom-up approach, especially for the first part of the talk. But if you had a little bit in mind of what's happening on the high scale, then in some sense, these vector-like fermions that you're adding should be parts of higher multiplets, so 5-plets or 10-plets.
Yes.
How would that change what you're doing?
So we've actually considered that scenario for vector-like leptons in my previous paper with Steve, where we have both the doublet and the singlet and all of that mix. So essentially what it means.
Sorry, doublet and triplet.
Sorry, doublet vector-like leptons and singlet.
Neutral singlet.
Oh, no, charge singlet.
So where would a charged singlet come from?
Um,
You mean a singlet under SU2?
Yeah, singlet under SU2, but charged under
Yeah,
U1.
so
I mean, that comes in, see, maybe 10 plus 10 bar of SU5, for example, where you have Q, U, and E bar, right?
so you say it's like E bar.
Yeah, it's like E bar, yes.
Bar.
Yeah, so it could come from 10 plus 10 bar of SU5. Yeah, so essentially, if there is both doublet and singlet, and if they mix with the Higgs, then the branching ratios essentially become free parameters. And that's how experiments should look for it. But I think the program is just beginning. On the other hand, for vector-like quarks, they actually do that analysis already, where the branching fractions of the vector-like quarks is essentially free parameters, and then they put constraints on them. So that would be the only thing. But I think with the E plus E minus collider, since we have access to mass peaks in different signal regions, we could still determine what's the branching fraction, and based on that, we can get a sense of where the singlet lives. If it comes in a multiplet, then we would expect a different branching fraction. So in that sense, an E plus E minus collider can really say a lot of things about just the structure of where it fits in. No question?
Okay, if not, let's thank Prudhvi again. Hmm.